We have a hospital has a nursing staff of 250 nurses. This is a scheduling problem. And they work in 4 shifts: shift A, shift B, shift C, and shift D. They tell you the times of the shifts. This is the shift A is the morning from 7 a.m. to 1 p.m. Shift B goes from 1 p.m., continues on 1 p.m. to 7 p.m. Looks like they have it broken down into 6 hours each. The number of nurses apportioned to each shift is based on the average number of patients per shift. Given the following table, use this information to solve the apportionment problem. So we have 250 nurses. This is the equivalent of having 250 representatives or 250 electoral college votes that we have to divide in a meaningful way into the shifts. Now, the person in charge here says, okay, well, it appears that shift B is the busiest shift. And that's the one that goes from 1 p.m. to 7 p.m. There's the busiest time. Well, to accommodate those patients, those busy times, we should probably give, a higher percentage of, assign a higher percentage of nurses to that shift so that the nurses won't become, overburdened with too many patients. Whereas shift D, which goes from 1 a.m. to 7 a.m., we don't have as many patients there. So we probably don't need to schedule as many nurses there. But we want it to be equitable. And so that in every shift, on average, a nurse is working with the same number of patients. They're not overburdened. All right. 19, 20, 21, and 22 basically just says, use the 4 methods that we've identified. Hamilton, that uses the decimal leftovers. Then we have Jefferson's, that uses a modified divisor and rounds down. Adams, that uses a modified divisor and rounds up. And then Webster's, that uses a modified divisor and rounds mathematically. So the standard divisor, that's what we give to D. And that's always the total population. Well, in this case, it's the total patients divided by the number of nurses. And if you think about it, this ratio makes sense. The number of patients per nurse. Okay, and so in order, we have to do this sum first, just this cell. And then we have to calculate the D. That's step number 2. And then we have to complete the standard quota, step number 3, all of those numbers. And then step number 4 is to complete all of the lower quotas, and step number 5 is to complete all of the upper quotas. So that's the order in which you want to do these problems. Then we get to the methods. And another thing that you'll notice here is that I didn't give you a value of D. So you're going to have to figure out what D can be. It's going to be very close to the D you calculate here. It might be off by a little bit. These are the first 5 steps, but they're also the quickest 5 steps. The harder work comes over here to think about the different methods. So in any one day, we have about 2,000 patients. That's what they're saying. So then we take the total number of patients that we just calculated and divide by the total number of nurses. All right, now I get the 250 because it's actually part of the problem. And this is equal to 8, right on the nose. And then we do the quotas. All right, the standard quota is the population of the state. In this case, it's the population of the shift, or the number of patients in the shift. It's this 453. And then we're going to divide by the D. and we're going to get the standard quotas. It turns out that all of these other methods over here do the same thing. You take the population of the shift, or the number of patients in the shift, and you divide by D. But the difference is that that D is going to be a modified D. It's either going to be a little bit bigger than 8, or it's going to be a little smaller than 8. Clear out these lists and then type in our populations. It's a little smaller this time. We don't have 5 different states. We only have 4 different shifts with those. And then we're going to take the L1 numbers, these guys, and we're going to divide by the common, or the standard divisor. So there's your 56.625, and those are the other ones. 43.75. And you should find that those 4 numbers do in fact add up to 250. Unfortunately, we can't give a fraction of a nurse to a shift. So we have to do whole numbers. So round down, just get rid of the decimals. 56, 81, 68, 43. 248. So if we just chop off these decimal pieces here, we will have assigned 248 of the 250 nurses to shifts. There's still 2 more nurses out there that need to be assigned to a shift. All right, upper quotas, just 1 more than the lower quotas. So this sum, since we've added 1 to each one of these, is 4 more than this sum. So this should add up to 252. We can't use the upper quota either, because then we would have a need of 2 additional nurses. So what are we going to do with those last 2? That's what this whole problem is about. All this work, trying to figure out where those last 2 nurses, which shift we need to assign them to. Okay, go ahead and put your 4 numbers in for Hamilton. How many nurses are you going to assign to shift A? How many are you going to assign to shift B and C and D? And remember, it should be close to one of these numbers. If you conceptually understand what's going on in this problem, then you'll say, okay, the big picture is I'm going to assign about 56 or 57 nurses to shift A. I'm going to assign 81 to 82 nurses in shift B because there are many more patients in shift B. And I'm not going to assign as many into shift D because we have fewer patients in the middle of the night. But we're going to assign 43 or 44, 68 or 69, one of these 2 numbers. Now, what's important about all these other methods is that however many that you assign, it has to, the total of all the nurses has to be exactly the 250. The only 2 columns that won't add up to exactly the number of nurses will be the lower quota and the upper quota. So our methods begin right here. This is all preliminary stuff. Here's the process. We have 248 nurses assigned. We need to assign those last 2 nurses to a shift. So which shift should get an additional nurse? That's the question we ask. We're not going to give two nurses to 1 shift because it would kind of lead us to violate the quota rule. So what we'll do is we'll give one of the nurses to one of the shifts and the second nurse to another shift. And the way that we're going to allocate it is based on the decimal piece left over from the standard quota. So identify all these decimal pieces and then award the first nurse to the highest decimal piece and then the next nurse to the second highest. So in most of these methods, you just kind of say, okay, you start with the lower quota. And we know that this adds up to 248. So you want to add one to two of these different shifts, and you're going to do that based on the decimal piece. So when I compare 0.62 and 0.2 and 0.37 and 0.75, 0.75 is the highest decimal piece. So I'm going to assign the first nurse to D. So instead of 48, shift D is going to get an extra nurse. So that takes care of D. D's not going to get the second one, so we just forget about D. Then we look at the decimal pieces that remain. And of the 0.625, 0.25, and 0.375, 0.625 is the highest, so we're going to bump this one up to 57. So we bumped 56 up to 57, adding one. We bumped up 43 to 40. All right, guess I should put my glasses on. It was 43, and we bumped it up to 44. And then 57, 81, 68, and 44 should add up to the 250. All right, let's go on to Jefferson's method. And let me just, if you don't have your notes in front of you, I'll just explain it to you here. What we're going to do is we're going to select a modified divisor that's less than. So D is going to be less than 8. Could be equal to, but less than. When you divide by a lower number, these quotients will be higher. So after we divide by a lower number, then we're going to round up. So Jefferson is choose a smaller number and then round up. Now the divisor is 8, so you want to go lower than 8. And you might not hit it if you go too low. So maybe we'll go 7.5. Now, if 7.5 doesn't work and assign all the nurses, the 250 nurses, we have to go back, and based on what we find, we're going to have to change this number. So that's why the calculator comes in handy, because we may end up dividing L1 by a lot of different numbers. I'm just going to do 7.5 here. So when we divide by 7.5, you get 60.4, 86.6, I'll just call it 7 maybe, and 72.9, and 46.7. Now, when you divide by a smaller number, these numbers will be larger, so we're always going to round down. We can already see if we round this down 60, we're in serious violation of the quota rule here. We should be giving 56 or 57. In fact, this number is so low that in every single situation, we're exceeding the upper and lower quotas by a huge amount. We're still going to round down, but still, we're way too high here, way too high here, way too high all the way around. Okay, so you want to go less than 8, but you don't want to go too much lower than 8, like 7.5 or anything smaller than that. So let me just give you this one here. Let's go to 7.93. See how much smaller it is than 8? Just 0.07. All right, so let's get rid of those. Those didn't work. And we try again. And divide not by 7.5, but let's divide by 7.93. So we're going to take all of these patient numbers and divide by a number a little bit less than 8, our standard divisor. And we get these numbers. All right, so 57.125, that rounds down to 57. 81.967, that rounds down to 81. 68.979, that rounds down to 68. and 44.136. That rounds down to 44. So if you add 44 plus 68 plus 81 plus 57, you get 250. So here's one solution. And notice that we have the number of nurses allocated is either equal to the lower quota or the upper quota. So this one went up 1. The number of nurses allocated to shift B is the lower quota or the upper quota. It turns out to be the lower quota. For C, it turns out to be the lower quota. And for D, it turns out to be the upper quota. But you're not going to see a lot of deviation between these numbers. They're all going to be very close. In fact, for Hamilton's method and for Jefferson's method, both methods led to the same number of allocated nurses. All right, now here's something that you can try. If you know that Jefferson's method worked with 7.93, 7.93 is only 0.07 away from 8. Then what you can do, Adam's method kind of does the opposite. You choose a D that is larger than 8 and then round up. Whereas Jefferson's method, we round down. And if you went down from 8, 0.07, one starting point for Adam's method is to go up 0.07. So why don't you try 8.07 and see if 8.07 works as a good modified divisor in this case. All right, and so as you're going through these methods, you're going to work out, you're going to first come up with a decimal number like these guys. But ultimately you want whole numbers because these represent nurses. And so once you get these numbers over here, then you're going to round them up. Okay, so now we're going to round up 57, 81, 68, and 44. Boy, it doesn't look like there's much variation in these methods, right? They're all given the same number. And that's so fine. That's fine. Sometimes that happens. Now, I'd recommend that you keep these numbers around. So you find a D, and remember for Webster's method, the D could equal 8, the D could be smaller than 8, or the D could be larger than 8. So it could be any one of those. So you could go above or you could go below on your modified divisor. And then the other difference is that for Webster's method, you're going to round mathematically. So if the decimal in the tenths place is 5 or higher, then you round up. And if the decimal in the tenths place is 4 or lower, then you're going to round down. So that's what we mean by round mathematically. Now you've already chosen here, I think you've chosen, well, 4, but at least 3, because the standard quota is this one over here with D is equal to 8. And then we did D is equal to 7.93. And then we did D is equal to 8.07. So you have the numbers for each one of those Ds. So what you could do is you could round this number mathematically. You could round this number mathematically, round this number mathematically, and same thing here, 44. And look at that, you get it. So you could use D equals 8 here, and it would work out. Let's go see if the next one works out. What if we used 7.93? We got that decimal. That would round to 57. That one would round to 82. This one would round to 69. And this one would round to 44. And when you add those together, you get 252. Okay, so D equals 793 is not going to work because it leads to too high of a number of nurses. And then we can try this 8.07 number. If you round this one, you get 56. If you round this one, you get 81. If you round this one, you get 68. And if you round this one, you get 43. And when you add those four numbers, you get 248. So you're under. So that's not going to work. So it looks like with D is equal to 8 and you round, you're going to find a solution there. All right, so it's a long problem, but what we're doing through the whole thing is doing a lot of rounding. We're doing a lot of arithmetic, dividing, but just conceptually know that, after you get to this point right here, all of these numbers are going to be very similar in each row. They're going to be different from row to row, but from column to column, they'll all be very similar. Chances are they'll all be either 56 or 57 for the first row, 81 or 82, 68 or 69, and so on. Many times the number of nurses that you allocate to each shift will not always be the same for every single method as it appears we found here. All right, the last thing, do any of the numbers in the table violate the quota rule? Do we see anything in this row other than 56 and 57? Nope, no violations there. Do we see anything in this row that is a number other than 81, 82, the lower quota or upper quota? Nope, they're all 81. 68 or 69? Nope, all 68. 43 or 44? No, all 44. So there are no numbers. No. All allocations equal the upper quota or the lower quota.